So what I'm going to talk about this session is about median finding algorithm. Okay, so Professor Pandurangan talked about finding min and second min, or min and max. In the morning he talked about min and max and went through very careful analysis to give a 3n by 2 minus 2 bound. Okay, the same thing will work. Yeah, okay. So suppose I want to find max and second max. Can somebody give me an algorithm? Okay, max and second max. This is after lunch. I have a job of waking you up, so I'm not going to move until somebody gives me an answer. I want to give me a simple pseudocode 3-line algorithm which finds maximum and second maximum. Do sorting and take, okay. Okay, finding second max. Sort and take the element in position 2, right? In fact, we can do this even for max, right? How much time will this take? How much time? N square? N log n. This is like breaking a peanut with a hammer. Okay? You can just do this, and I'm just asking you for one element, you say, okay, sort it. And obviously, this is an inefficient algorithm. Somebody else, give me a different algorithm.
You start with the first two numbers, decide which is the maximum and the second maximum, and keep track of.
Exactly. So you start with some, let's say, compare A1 and A2, and let's say if A1 is greater than A2, then we say max is A1, and maybe second max is A2. Otherwise, max is A2 and second max is A1. And then you have a loop running over all the elements, other elements, doing what?
Okay, first we can compare it with max.
Okay.
And if it doesn't turn out to be the maximum, then we compare it with.
Right. So how much, what will be the worst case number of comparisons here? 2 for each. In the worst case, because you may have to end up with comparing with both. So 2 into n minus 2 plus 1. This comparison, right? So this is like 2n minus 3 to find the second max. Okay. Now, that's fine. Okay. Now, if I want to find the third max, what do you do? Do the same thing, right? Keep 3 elements, run through the loop. You might end up, 3 into n minus 3 plus 1 and so on. So it's like, if I want the case from the top, then roughly this algorithm would be something like k times n comparisons, right? So is that the best you can do? Can you do better? Well, let's just go back to finding second max and see whether there is a better algorithm. Yeah. So what do you do? So let's go back to max finding. Give me a different algorithm for finding max. One algorithm is, okay, I make the first element as the largest, temporarily go through the loop, comparing everybody with this, and then I get the max. That's again n minus 1 comparisons, sort of a sequential. Can you think of a different algorithm for it?
Take pair of max and then follows max, then take a pair of that.
Yeah. So this is like running a tournament. I want to run a tennis tournament and pick the champion. I'm not going to play one, I want to do in parallel and a few number of days, as few days as possible. So I'm not going to wait for the winner of the first match and then play the next one. I can parallelly, pair them up. I compare them all, and then the winner of these first round will move to the next round, pair them up and keep going. Finally, I get my winner. How many comparisons will that take? Okay. Okay, I mean you have to worry about what if n is odd, or if it's, or it becomes odd somewhere in the middle and all that kind of thing. Okay, now Pandurangan did gory details of floors and ceilings, and Vikram and I are happily avoiding, and we worry only about assume n is a nice number, power of 2 and all that kind of thing. Then how many comparisons? Let's see, how many comparisons in the first round? N by 2. How many in the next round? N by 4, n by 8, and you add them all, what do you get? N minus 1 again. It's a geometric series, so it's also giving you n minus 1. Okay? So you have a tournament like this. So you have this, pair them up, moving to the next round, and finally, this is the finals, and this guy is declared as a winner. Okay? Now, normally in such tournaments, the runner-up of the finals is also declared as the second champion or something, right? That's obviously not correct. Can I just say that, play, this is some x and y, and whichever is larger is the largest at this point, and whichever is smaller is the second largest, is what is normally declared when you run tournaments. Okay? Now, several people are shaking their heads, so obviously this doesn't work, right? Can be, yeah? What's example?
The first match itself, maybe the second largest played against the winner.
Yeah, so I might have like this, the winner moves here, and then 8, 4, and 8. So the 8 is the largest number, and 4 is far from being the second largest. In fact, there are several others which are larger than 4. Okay? So it was Lewis Carroll, who is the author of Alice in Wonderland, who seemed to have, the history shows it, pointed out the unfair method of declaring the runner-up of the finals as the second largest, and that opened up the whole thing about finding. Okay, so given all this, suppose I've run a tournament, I've spent n minus 1 comparisons. Now I want to find the second largest. What should I do? With this information, what I have on the tree, which has stored the outcome of the comparisons I have made, I want to find the second largest.
Take all the numbers who have played against the largest at some point. Among them.
Okay, did anybody else get that? So who are the candidates for the second largest? Let's see, right? Anybody who played against the largest in the first round, think of it as a first round tournament you have done. Anybody who lost to the largest, got eliminated, that person can be a candidate for second largest. Why? Is it easy to see? Well, anybody else is not a candidate for second largest is easy to see. Why? Because they got eliminated because they played with somebody else who lost to the largest. Okay? That means there are at least 2 guys above them, so they cannot be second largest. So the only candidate for the second largest are all the numbers that played against and lost with the largest. So with this tree of information, if I have, 8 is declared winner, then my candidates for second largest, somebody who played with 8, somebody who played with 6, somebody who played with 8 in the previous round, somebody who played with 8 in the first round. These are all the candidates, and now I just go and find the maximum among them, and I'll get the second largest. How many candidates are there? Log n, right? 1 in each round, there are log n rounds. So what you can get is, by using this algorithm, you get right? You run this tournament, and then of course it requires certain bookkeeping. I have to remember things and so on. Ignoring those details, I just need, there are only log n candidates, I can keep track of them and find the maximum among them, and I get my second largest. Now this whole thing again can be applied if I want the third largest. Okay, more bookkeeping is required, gets messy, but there's a very clean way of doing the whole thing. To find kth largest in k log n comparisons. Does anyone know how to do that? Order k log n, I'm ignoring. So what you do is build a heap. If you know what it is, fine. If you don't know, don't worry about it. It's a way of storing this bookkeeping information. So you build a heap which can be done in linear time. In linear number of comparisons, you can build a heap, and then you just delete max k times, and each one takes k log n times, so you get k log n. Okay, so in general, you can build a heap using about 2n comparisons for So build a heap and then do delete max, and you get your kth largest. But you actually get a lot more. All I want, suppose, is only the kth largest. I also get the largest, the second largest, third largest, and everything up to k. Okay, so this is still better than the naive, which simply said, go over these guys k times, and pick some k elements as candidates and run this. That was kn, and this is like k log n. Okay. So k small, 3, 4, it's fine. It's all linear time. But if I'm talking about k close to median, n by 2 or n by 10 or some such thing, then that algorithm is an n log n algorithm. Now, so the question which was open, which was an interesting question in 1970s, when people are doing large amount of data processing and all that, is that can you actually find the median without sorting? Because yes, you can find it without really sorting. I found it, but can you do substantially better than n log n time? In particular, is there a linear time algorithm for median? Okay, so this was a question that was asked in 1970s, and in 1973. There are 5 authors: Blum, Floyd, Pratt, Rivest, and Tarjan. It's sometimes called BFPRT algorithm. They showed that you can find now just median any k largest for any k in order n time. Okay. Now we check that except Pratt, all of them have won Turing awards. Blum, Floyd, Rivest, Tarjan. This is the highest award in computer science. So it required, not for this work, of course, but the point is that it required these 5 great minds to get together and come up with the linear time algorithm. And this is a textbook stuff now. You all learn in your 3rd year course or some such thing. Okay. So the point of my session in the next half an hour or so is to go back to those time of 1970s when this algorithm was not there, get into their heads and see how they designed this algorithm. Okay. So this is one of the complicated algorithms you will see in your early algorithms course. You'll have this big picture. People would have seen some blocks of 5, median of median, all kinds of things, and then do some various parameter manipulation. They got this linear time algorithm. But armed with all we learned today morning about recurrences and divide and conquer and all that, that was the thing that was available at that time. Reverse engineer the algorithm and sort of explain you how they arrived at this algorithm. Okay, so that's the point of my session today. Okay, so let's just go back here. I'm after getting a linear time algorithm. Let me just go and look at these recurrences and see what gives me linear time, right? So I'm going to go from here. Not, here is an algorithm, analyze. No, I'm not going to do that. I want to get a linear time algorithm for this problem. Let's look at some recurrence that gives me that. Okay. So here is, let's look at this recurrence. Okay. Yeah. So let's say dn. No, let's keep to Cn. So d of n is basically some linear function, C of n, and a is 1. Let's look at this recurrence relation, and the master theorem tells you that n, so what is alpha? What is alpha here? Log a to the base b. What is it? Yes, 0. A is 1, right? A is 1. So log a to the base, whatever b is, log of 1 is 0. So my alpha is 0. So the function, what are we calling that function? Watershed function. I was hearing it first time. So that's n to the alpha, which is like 1. Okay, that's the function. And what are we comparing it with? D of n, which is linear, right? Some Cn. And it falls into this because d of n is omega n to the alpha plus epsilon, because n to the alpha is just 1. It's much more than the constant, which is what this driving function is. So T of n is order d of n, which is order n. Okay, so here is a clue for a recurrence relation that gives me a linear time algorithm. Okay, so I want to get, so what does this tell me? That in linear time, I want to reduce the problem to a recursive problem of a fraction of the input. Okay, in other words, in linear time, I want to throw away a fraction of the input. If I manage to do that, then I have a linear time algorithm. Okay, in linear time, throw away a fraction of the input and reduce to a recursive problem on this remaining input. Okay, so let's write that down. Okay, so reduce the problem recursively on an input of size n by b. Some fraction, okay, whatever. If you manage to do that, we fall into this recurrence and you have a linear time. Okay. So this was something available to them at that time. They had seen these recurrences and solutions. Okay, so this is what we need to get it. Okay. The other thing we know is some version of quicksort for finding median. Okay. So how does quicksort works? Well, you just pick a random element, partition all elements into pull them less than that, greater than that, and recursively sort each portion, and it works well on the average. If I want to adapt some sort of a similar idea for finding the median, what should I do? Let's write this, right? So find a random element. Remember, now our goal is not to sort, but to find some kth smallest element, okay? Because I think I'm going to just talk about kth, because in the recursive situation, I may not necessarily be finding median, but some other element of some rank k. Okay? So find a random element x. Partition all elements with respect to x. Okay, so my entire list is split into L less than x, x, L greater than x. Okay, let's assume all elements are distinct and you don't have to worry about tie breaking and all that. So this is the next step. Now what should I do? What is the recursive step? I want to find the kth smallest element. Okay, I'm comfortable smallest. It doesn't really matter. Let's say kth smallest element. That means kth from the left in the increasing order. So what should I do? See the size of. So if then what can you say? X is the answer. X is the kth smallest element. What is the kth smallest element? They're exactly k minus element. If you are lucky and it turns out I picked a random element, found its rank. I compared by comparing that with everybody else, and if L is equal to n, return x. Else if then I want to find I want to recurse in this portion. My kth smallest is inside here, right? So return, or basically I want to find the kth smallest in the list L, then return kth smallest and else. Otherwise, this L, so what I have is, suppose this is very small, it's less than or equal to, find so in that list, go and find an element of this rank in that right position. So it's a recursive algorithm. Okay, let's so how much time does it take on this step?
-1 for x.
Okay. How many comparisons are made here? Order of n, actually n minus 1, because x is compared with everybody else. So this is an order n step. Remember, this is a goal. Okay. So I have done a partitioning, I have done some linear time, and I am into a recursive problem. Okay. The only problem is that I don't have a control on these sizes. I mean, I would be lucky and I'm done if I manage to throw away a fraction of the input in this process. But this was a random element, I don't know. It could be the smallest element. It could be the second smallest element. So I just end up throwing one element, and everything else is there in my recursive thing. So this is not good enough, but it's not very hard to see that it works very well on the average, because I'm just picking a random element. What is the chance that it is in this range? Let's say this is an element of rank n by 10. This is an element of rank 9 by 10, and I pick a random element. What is the probability that it's going to fall here? So 8n by 10 out of n. So it's like 4 by 5. Very high probability it's going to, because if it falls here, I'm already done, because I end up throwing, depending on whichever side it recurs. Either I recurse here or there. Either I get to throw away this portion or get to throw away this portion. So I'm throwing away a fraction of the elements. Okay, and that happens with very high probability. And so one can actually do a formal analysis of this and show that expected running time of this is linear. Okay, because of this exact constant linear time, and a fraction of the input is where I'm recursing. But now I'm talking about working for a worst case. So what I want is so I want these portions where I am recursing to be is such that some fraction of the elements are thrown away. Okay, so essentially what I would want is, instead of randomization algorithm, I'm talking about deterministic step. What I want is find an element of rank between for 3n by 10 and 7n by 10 in some Cn time. Okay, I mean, I could just use any fraction here for that matter. Suppose, okay, so what I wanted this element I picked to be that in both sides of the element I should have some fraction of the elements, so that when I find the rank, partition it and recurse, I end up throwing at least a fraction of the elements. So let's say I manage to find an element whose rank I don't know. For some reason I don't know what exactly its rank. I have to run this step to find it, but I have a pretty good hunch that it is, suppose, between 3n by 10 and 7n by 10 rank of that element. Okay, if I manage to find an x in this range, in this step in linear time, then after this partitioning, wherever I recurse, I get to throw away at least this portion or that portion, and I'm in business. I get into this recurrence, I get a linear time. Okay, so this was their first approach. Okay, and the reason they felt it's possible is, oh, this random pivot thing works, so maybe I want to find in linear time an algorithm whose rank is, not necessarily 3n by 10 and 7n by 10, but some fraction, some n by b and another n by c or something like that. And they did not succeed in finding such a thing in linear time, because it amounts to again finding another kth smallest element, and that's the problem we started off with. Okay, so they went back and looked at this recurrence again. Okay, well, this recurrence doesn't give me a linear. I mean, I would like this recurrence to give get me an algorithm of that type, but somehow that didn't give. But let's see, can I extend this recurrence and still achieve linear time? Okay, so they tried the following. Okay, so this is one. Let's write T of n Okay, in the morning recurrences were all, the problem was divided into almost the same sizes. But suppose I have a recurrence of this form. What condition should I satisfy on the A and B to get a linear time here? Okay, suppose 1 by A plus 1 by B is equal to 1. Then what do you know? Do you have an example of such a recurrence you've seen? Is there a recurrence you saw in the morning which is looking like this, but 1 by A and 1 by B equal to 1? Merge sort, right? Half plus half. Two problems of size n by 2, and that was not giving us linear time. That was n log n, right? So 1 by A plus 1 by B equal to 1. Actually, one can prove that it doesn't. It actually gives you n log n. But suppose it's strictly less than 1. Then one can prove that this recurrence solves to linear time. Okay, I'll sketch the proof using one more method than whatever you have seen in the morning, just by something which we know, induction. Okay, so I'm going to guess that this is a linear time. I mean, there is a base case and all that. We will guess that this recurrence solves to linear time, and try and prove by induction that it is linear time. Okay, and see where we critically use the fact that this is strictly less than 1. Okay, so proving by induction is just easy, right? So base case would be like, T of n is some large constant for n less than or equal to another big constant. Okay, that's a base case. So so the induction step, what do I want to show? I shouldn't use k, alpha n for a constant alpha. This is the claim. Okay, so how do I prove by induction step? Well, assume the induction hypothesis. Then what do I need to show? Tell me. What do I need to show? So I have this recurrence relation. I want to show that T of n is less than or equal to some constant alpha times n. And let's assume it to be the case for small values of n, smaller values of n. That means it's true for this or this. Okay, I'm trying to use this, right? And this. Okay, so to show what? Alpha k n by a plus alpha k n by b plus cn. I want it to be less than or equal to k. Yes, are you with me? K is the constant which we will choose. Sorry, where is k coming? alpha n by a plus alpha n by b plus Cn, I want it to be less than or equal to alpha n. Right? And there is such an alpha that satisfies this is what I want to show, then I would be done showing linear time. Right? Okay. I mean, you can also expand this recurrence. So how do you show this? Let's say if I put n by 2. How do you show this whole thing solves to linear? It's Cn plus Cn by 2 plus Cn by 4, and it's a geometric series, so it's 2Cn. Okay. Similarly, you can just go and expand it out and write your recursion tree, and the whole idea of, again, you'll get some geometric series that will add up to linear. Okay. But I'm just giving you yet another proof by induction, and particularly to see why I need this fact that 1 by a plus 1 by b is strictly less than 1. Right? So I want to show this. Okay, so let's get rid of n. So I want alpha into 1 by a plus 1 by b, or rather or I choose alpha to be greater than or equal to C is this running time, whatever time I spend on this step. So if I choose alpha to be greater than or equal to this, then that will satisfy this inequality. That's all I need to. And you can see why I want 1 by a plus 1 by b to be strictly less than 1. Okay? Yes, I don't see some happy faces. Is it clear? So essentially, all we are saying is that we know that if you spend linear time and a fraction of the input, it solves to linear. You can generalize this recurrence to spend linear time and multiple fractions, but they all add up to less than 1, just like this half was less than 1. Then also this whole thing solves to linear time. Okay? And you can prove by induction, you can prove by solving recursion tree and so on. And so now this gave them a little more leeway now, right? Let's come back here. So now I'm armed with some such recurrence, right? So I come here now. I don't need to find such an element in Cn time. I can actually use Cn plus another recurrence, another recursive thing, right? So suppose I manage to find it in, let's say, Cn plus some t of n by 5 or something. Okay, and after doing this, it so happens. So how much? What would be what can you say about suppose that element I'm looking for is in this range, then what can you say about the maximum size of the portion where I am recursing? How much can that be maximum? Who said 7 by 10? Yeah, okay. Is it clear? Because I end up throwing at least 3 n by 10. Whether I recurse here or recurse here, I end up throwing it. If I manage to find such an element, I have to explain how you do that. If I manage to find such an element, not just in Cn, suppose I also spend a little bit more time, then what will be the running time? This is the overall running time. Okay. Now n by 5 is okay, because if you add this fraction and that fraction, this is 2n by 10 and 7n by 10, just less than 1. Okay. And you can play around with various parameters and see why it works. Okay. So now I'm going to just explain this step, how to do this. Okay. Then that's their magic first step, and after that everything else follows. Okay. So now I'll tell you, that's this big picture of blocks of 5 doing all this median of medians and all things. So that because you find such an element where you can throw away a fraction of the elements, that fraction is not just any fraction, this fraction plus this fraction add up to less than 1. Then you have a linear time solution. Okay. So how do they find this? And that, let's just go back and do this. So step 1 of the goal is this. Okay. After this, I'm going to partition all the elements. That's n minus 1, and then I know that if I manage to find such an element, then I end up my recursive portion to have size at most 7n by 10. Okay, so what do they do? Well, and let's go back and draw this picture. So divide your input into blocks of size 5. Okay. So there are n by 5 blocks. Right? Again, what if n is not a multiple of 5? Then maybe keep a bunch of elements aside and then do your comparisons later on. We won't worry about these details, but it can be worked out. Because my goal is to just get to how to get this in this much time. Okay, so step 1. So divide the list into blocks of size 5 each and find the median of each block. Okay, so the median out of these 5 elements, do your comparisons, find the median. How do I find the median? Well, do whatever you want. You can sort, because this is a constant number. If you want to spend 10 comparisons on this, feel free, no problem. At the moment, we are not worrying about the constant in the linear time we're aiming for, but that's for later. You can optimize it. So this takes, even if I just do sorting, I'll get n by 5 into 10. So this is like 2n. Okay. Next step, find the median of medians. So I have done these comparisons and I got these medians. How do I find this? This is too many elements, n by 5 elements. How do I find the median of medians? Well, I am allowed this leeway, right? So recursively. That median is that x, and then you follow through that. Okay, then you got your x. I claim that x you got satisfies this. Okay, then you can partition x, compare everybody, find its actual rank, and recurse on the appropriate portion. Now you'll argue that the x I got actually is somewhere close to the middle. See, the problem with the quick select was that the pivot you picked comes so close to the boundary, then you have not done your split carefully, right? But I claim that by doing this little pre-processing, I managed to find an x which is not too far close to the boundaries, extremes. And why is this? Well, let's see what is the property of x. There are at least n by 10 elements in each side. Because this is a median of n by 5 elements, there are at least n by 10 elements smaller than this, at least n by 10 elements larger than this. And not that much alone. For every element larger than this, there are 2 more elements larger than that element, right? Because I have picked that guy was a median of some 5 elements. So for every element you have larger than that x, there are also 2 more elements larger than that. So actually there are, x has at least 3n by 10 elements larger, and by the same argument at least 3n by 10 elements smaller. Okay, so is it clear? For every, there are n over 10 elements smaller than this, n over 10 elements larger than this. Okay. Now, suppose here this was one element larger than this. But remember, this itself is a median of this block of 5 elements. What does that mean? This element has 2 elements larger than that and 2 elements smaller than that, right? So in particular, for anything larger than that, larger than x, there are 2 more elements larger than that element and hence larger than x. So all the 3n over 10 elements are larger than x. Similarly, for every element smaller than x, there are 2 more elements smaller than that element and hence smaller than x. So there are 3n over 2 elements smaller than, which means that's exactly what I wanted, that I've picked x in a way that at least, right, it's not, at least some 3n by 10 elements are here and at least 3n by 10 elements are here. So after you do this split and you're going to recurse, you are guaranteed that some 3n by 10 elements are thrown out, at most 7n by 10 elements left, and then you can add them all less than 1. Okay. Now that's it. That's end of linear time algorithm. So this was Bloom-Floyd Pratt reverse Tarjan linear time algorithm, and so it's you get the idea of what they were after. This is the case of recurrence relation driving an algorithm. Okay? We saw examples even in the morning where the 4 to n by tn by 2 was not enough for matrix integer multiplication, and you have where to go and improve, right? So it's like recurrence relations and the algorithm going hand in hand. So let me just stop with a couple of exercises. Well, the exercises are why blocks of 5, right? It's good to choose an odd number so that the median is very well defined. You don't have to worry about this or that. So let's choose an odd number. Does it work if I pick blocks of size 3? Well, we have the entire machinery there. Let's go and analyze it, right? If I choose blocks of size 3, then what happens? How much time? This is a linear time, whatever it is. Okay, may not be 2n but something else. This would be tn by 3. So what would be my recurrence? Some cn plus, okay. And what are these numbers? What can I guarantee? To n by 3, because it's a median of n by 3 elements, so n by 6 elements are in each side and each has one more, so 2n by 6, it's n by 3 is what you can guarantee to throw out, so 2n by 3 will be left out, so what you have is this, and this doesn't give you linear because the fractions add up to exactly 1. Okay, does 7 work? So if block sizes are 3, if they are 7, let's see. So I'm doing a median of the medians. Let's see. So n by 14 on each side and 4. So 4n by 14. That's 2n by 7 thrown out, so 5n by 7 left out, which is fine. Is this right? I mean, I just quickly did, I don't know. Yeah? Okay. So that works. But then you can, plug in and see the constants vary. Okay, 5 gives you better constant than 7, I think. Yeah, so this was the original, 1973 median finding algorithm, and since then it has gone through evolution of improvements on the constants, and currently you're saying from the morning?
No. Is it order statistics by pruning?
Order statistics is by?
Pruning. That means you have to arrange the numbers and then you go on and neglect.
Well, this is finding median,
Yeah.
whatever that is. I don't understand order statistics by pruning. This is a problem of finding median. Okay, and so the current best bound, and the lower bound is also an interesting. I mean, Pandurangan mentioned about 3n by 2 minus 2 as an upper bound for finding min and max, and there is a matching lower bound using some adversary arguments that can show that any algorithm will necessarily take that many comparisons in the worst case. For median, currently the upper bound is less than or equal to 3 minus epsilon n, and there is a lower bound of some 2 plus epsilon n. And the epsilon is a fixed constant. So I think this is some 2.95 n and 2.05 n lower bound or something. This is still an interesting open problem in narrowing down the gaps. And there have been several papers on this about improving the constant and improving the lower bound. Okay. Yeah, I think I'll stop here. Any questions, comments?
How much is the constant C in this?
More than?
3.
Oh yeah, it's some 2-digit for sure. at least 10 or this C.
10 times C.
Yeah. Oh, you're saying what is this C? This C, you have it, right? For the 5, it's just 2n. There's nothing else. There's 2n plus n.
Plus n, so
3n. So it's about 30n, is it? That's your calculation? Okay. Okay. Thank you.